Here's another sum of products example. Here we are given the truth table for a sort of real world example problem, and we need to find the Boolean expression. So we can use the sum of products method to find the Boolean expression. The first step is to make the truth table. The next step is to identify where the output is 1. So that is actually already done for us here. The output is 1 for all of these lines. The next step is wherever these outputs are 1, write the products. The products are the inputs. And wherever we see a 0, we are going to invert an input. And then the final step is to add all of those products together. So therefore, the output in this case, Z, is equal to the sum of all these products. There are 4, 8, 9 products. So let's write down what that is then. The Boolean expression that describes this truth table is the sum of all these 9 products. And it's the sum of them all, or it's actually the OR gate of all of these ANDed factors. Now I have to transcribe the inversions. And I hope to not make an error in transcribing, but we all make mistakes. The last one has nothing inverted. So our final step is to simplify this. Do you want to build this expression? This is a massive expression. I don't want to build this expression. Let's see if we can make this into a smaller expression. So the first thing we want to recognize is that we can factor out we do have, there's quite a few approaches to doing this. I'm going to take one that is similar to the example that I gave you in the textbook, but a little bit different. I'm going to leave the first term the same, and I'm going to recognize that I have D inverted plus D, D inverted plus D, D inverted plus D, D inverted plus D in all of these. So what I'm going to do is I'm actually going to factor out D inverted plus D from all of these other factors. And what I would be left over with here it's hard to write it this way. I'm going to have to write it. I'm going to have to write what I'm left over with. Because in both of these, in this and in this, I'm going to have to factor out what is similar. So what is similar here is A, B inverted, C inverted. What's similar here is A, B inverted, C. And what's similar here is A, B, C inverted. And what is similar here is A, B, C. And those can all be multiplied. Those are all factored out, and when they factor out, you're left with D inverted or D. Okay, and D inverted or D, that's an OR gate. And when something that is a 1 or a 0 go through an OR gate, of course, one of them is going to be a 1, so that's going to turn into a 1. And when we AND something with a 1, then it's just like it's sort of the same as saying the thing itself. So A, B bar, C bar ANDed with a 1 is the same as saying A, B bar, C bar by itself, because whatever the output is the same as that input. That's another one of our theorems. So we can simply get rid of the 1s. And if you're not following this, then I do recommend going back to the simplification lectures. So there we go. We have simplified the terms considerably here. And now I see some more sort of common factors. Let's see if this works. Nope. I see AB. Sorry. Oops, I have a problem on this. I see AB bar. I can factor out here, and I see that I have AB. I can factor out on these two. AB bar, and I can factor out AB on these two. This first term is just kind of going along for the ride here. And here I'm left with C inverted or C, C inverted or C. Of course, C inverted or C is equivalent to 1 because it's an OR gate. One of them's a 1, one of them's a 0. So the answer has to be a 1. So we don't really have to write it because we know it's ANDed. So the output must be the same as the input. Here again, I can recognize that I have this B bar plus B if I factor out A. So I can factor, oops. Here I can factor out the A's and be left with B bar or B, which conveniently helps us in exactly the same manner as we have been doing this whole example problem. Factoring out A leaves us B inverted plus B, which again with the same theorem turns to a 1. And when that turns to a 1, of course, the output is going to be the same as this input A going through the AND gate. And I can't see anything else to do in this problem. So this is the answer. Now, let's take a step back and see what we have accomplished. What we've accomplished is that we've taken this truth table and use sum of products form. So we summed up all of these products. We got this massive expression that we did not want to build because that would be very expensive. We used our theorems to simplify, and now we only have to build this, which is less expensive to build. So that was an example of sum of products form on a somewhat larger expression.